Okay, so we're going to start chapter 8 today. Now, chapters 8 and 9 are relatively short. Like, after tomorrow, we'll be done with chapter 8. And then Thursday, we start chapter 9. So, for AP, your chapter 8 and 9 tests will be together as one test. For dual credit, that means y'all are going to test with AP next time because we will have been through all the test through material. So everyone tests next Wednesday again. Next Wednesday. And part of that's because dual credit, y'all have already covered 40% of the next test. When we did, remember that section 7.6 that I said that this is going to be on test 3? Yes. That's 40% of test 3.
Can I ask you a question? Really quick. So, like, I'm not gonna pull it out right now, but like the homework that's due tonight, I feel like I'm not doing it right because like it just seems like is it just z equals x minus mu over sigma? Is that pretty much all you're doing the whole time?
Yeah. That's all.
I thought I was like a 0 on it. I was doing like everything the exact same way. Like within those like 3 problems that you showed us.
Yeah.
It all looks like I was guessing almost. Oh, actually, I know. Sorry. Before you calculate the score, like before you go to the chart, the actual score, you need to round up that number or leave it the same.
It depends on what your next digit is.
Like if it's like a negative 1.57, I can go to 5, 7, 8. I can go to 5 and 8.
Okay, you round it up. Yeah.
I was just making sure because that's how I was doing it, but at the same time I was thinking maybe he wanted us to be more exact with it. I wasn't sure. All right, thank you.
You could be on your calculator, but I'm not going to. I don't want. I'm already giving y'all way too much. So I don't want to give y'all something else, and then it's like, okay, what way do I do it? Just give you one way. If you figure out the calculator way, I have the answers in there for the calculator too. But that's going to be more of a figure it out on your own and ask me if you're correct type deal. Okay, so chapter 8, we're going to look at sampling variability and sampling distributions. If my board will work. So our goal today is to get through 8.1 and 8.2. We should be able to do that.
We're going to have time at the class?
At the end of class?
Yes,
probably not.
Okay.
I'll say that. It depends on how well y'all do in our little activities that we're going to do. Okay, so let's suppose that we're interested in finding the true mean fat content of a quarter-pound hamburger from a national fast food chain. So maybe it's McDonald's, maybe it's Burger King. Pick your favorite chain. I would say Whataburger, but they're not national.
Are they?
Are they?
Yeah, Chicago bottom. Some company in Illinois bottom.
Oh, that's right. So they're getting that way at least. You're right. It won't be the same.
JJ won't try to buy that.
So to learn something about mu, we can obtain a sample of 50 hamburgers and determine the fat content of each one. So some of the questions that might come to mind as we're doing this, and we're not going to have answers for them right now, what would be a good sample mean? How close to the actual mean is our sample mean? Will other samples have the same mean? Bless you. To answer these questions, we're going to examine the sampling distribution, which describes the long-run behavior of sample statistics. So remember that the sample mean is a statistic. A parameter, if you remember, is talking about population. Since we're dealing with the sample, that's going to be a statistic. So there's two blanks on this slide, if you didn't notice it. Long-run behavior and statistic. So just to recall what a statistic is, it's a number that can be computed from sample data. So in basically this week or so, our sample statistics that we're going to use include X bar, which is our sample mean, S, which is our sample standard deviation, and P hat, which is the sample proportion. And like I said, you read this P hat, almost like a slang way of saying fat.
Really what it's called is P hat.
Yes.
Like that's not like make it easier term. Like the mathematicians call it P hat. Is that because it looks like it has a hat on it?
Well, that's what that little anytime you put that over a leather, that's called a hat. Yeah. And then this is this mean right here. You read it X bar.
All right, I was just checking.
Yep. Oh, too fast. The observed value of the statistic depends on the particular sample selected from the population. And it will vary from sample to sample due to sampling variability. So hopefully we'll remember this because we spent at least a day or two talking about it. But remember when we talked about catching all those fish from Lake Sam Rayburn? Yes? What did we say when I asked y'all? If we all went out and we all caught fish, would we come back with the same average? No, we wouldn't. That's sampling variability. We're all getting fish from the lake. Hopefully no one's going to Toledo Bend, getting a fish, throwing it in Sam Rayburn and saying, look what I caught. So that's sampling variability. So let's look at the campus of Wolf City College's pond. They have a fish pond with 20 fish in it. And somehow they know the length of every single fish in there. So the lengths of the fish in inches are given below. Let's suppose we randomly catch a sample of 3 fish from the pond, measure their length, and then get the average length from those 3. So let's say the first 3 fish we caught were 6.3 inches, 2.2 inches, and 13.3. How could I find the average length here? Add them all together and divide by 3. So I can say that X bar is equal to 6.3 plus 2.2 plus 13.3 all divided by 3. If I did that, what would I get for my mean? Let's do 2 decimal places. 7.27, good. That is an example of a statistic. That's not the mean of the whole population. That's just of that sample. So let's catch 2 more samples and look at the sample means. So second sample, we catch a fish that's 8.5 inches, 4.6 inches, and 5.6 inches. So I'm going to find the mean of those. So add them up and divide by 3. .23 inches. Good. And then we're going to have a third sample. We're not satisfied with those 2. We want to get a third. We want to keep fishing longer. So we're going to do 10.3, 8.9, and 13.4 inches. .87 inches. Speaking of fishing, totally random, but evidently catfish like Cheez-Its crackers, in case you didn't know that. A friend of mine has a pond that they stock catfish and bass in, and one day they accidentally spilled a bag of Cheez-Its into the pond. Like all the fish just started coming up and swarming all the Cheez-Its. So, what's that? Could be. Okay, so let me erase my writing here, that way we can see the box that's about to pop up. Now, the true mean, if we added up all 20 and divided by 20, we would get that the true mean is equal to 8 inches. So notice that our sample means, some are close to 8, some are further away, some are above, some are below. They're just kind of all dancing around the true mean. They're not all the same. This is what we call sampling variability. So let's flip over to the next page. So sampling distributions of X bar, the definition of that is it's the distribution that will be formed by considering the value of a sample statistic for every possible different sample of that size. If I was wanting to sit here and estimate the height of this class, I could sit here and pick samples of 2. The sampling distribution would be the average of every possible combination of two people type in this class. So in this case, the sample statistic is the sample mean, which is X bar. Okay, so continuing with our fish example, yes. Back. Oh, why isn't this working? There you go. So if we picked, or if we figure out how many possible samples of size 3 we could get, it would be over 1,000 samples. So if we were to catch all those different samples, calculate the mean length of every sample, we would have a distribution of all possible X bar values. We would also be fishing for a really long time. This would be the sampling distribution of X bar. And we're going to get a little bit of practice doing that at the beginning of section 8.2. So, any questions on this example? Okay, section 8.2. We're going to look at the sampling distribution of a sample mean. So in chapter 8, there's going to be two that we're interested in. We're going to do a sample mean, and then tomorrow we'll look at a sample proportion. So let's get through the mean first. Now, I don't know about y'all, but I don't want to sit there and list all 1,120 combinations for that first example. So we're going to cut the fish down to only 5. There's only 5 fish in our pond, and we're given the links below. That way, as we go through these next 2 exercises, we can find all possible samples in a realistic amount of time. First, let's figure out the mean and standard deviation of the population. So I want y'all to put these 5 values into L1 in your calculator. Put those into list 1 in your calculator. And
That's L1, right?
yes. And run the one variable stats.
That's, how do I get there? Second 9?
So are we trying to clear it, or are we trying to get to L1?
I'm just trying to get to L1.
You hit stat.
Edit, okay, I got you.
And then edit.
What's the list like?
We're just doing those numbers?
Yep. And then once you enter the numbers, you'll go to stat, compute, or calculate, sorry. Stat, calculate, and then one variable stat.
Neat.
How do you get what? Okay, so you go to stat, over to calculate, and then one variable stat. That's the sample standard deviation. But this is our population. We don't want to do that. Let me give you everything. Anyone need help on this? If you enter them in, what do you get for the mean?
That was mean, 7.84. No,
7.84.
where can we put this? Where it says, what is the mean? Okay, guys.
Yep. Where it says, what is the mean?
So here is going to be X bar, or is it going to be mean?
So it shouldn't have a bar right here because we're doing population. I just haven't edited the PowerPoint to get rid of it. So it should just be mu of x because this is our population.
So mu is for population, and then X bar is for sample.
Yes.
Okay, I just got to remember that.
Yep. Now, what's our standard deviation?
Standard deviation, that is 3.65. Wait, no, sigma, 3.26.
3.262. And again, this should be sigma of x, not x bar.
Oh, my bad. I read the one that said S. Which one is that again?
S is your sample standard deviation.
It got me again.
So hopefully you wrote those up above because now we're going to need to do a couple exercises here. Does anyone need me to hold up for a second before we go to the next part?
Instructions. L1.
Do we have to do 3 decimal places?
Yeah, let's do 3 decimal places.
L. Alright. Thank you.
Okay, so maybe you wonder why do I have a blank slide up there? Well, that's because I don't have room to do what we need to do on the other slide. So I'm going to go to it and then go back to my blank slide. They want us to find all the samples of size 2. So go back. I don't want us to see the answers yet. So I'm going to go back to my blank slide. We want to find all the possible pairs that we can have. I'm going to write up here pairs. And then let's go through this in a systematic way. In other words, don't just start naming pairs. Let's systematically pick all of our pairs. So let's start with 6.6 and freeze it in place, and then get all the pairs that go with it. So 6.6 and 11.7. And we do 6.6 and 8.9. 6.6 and 3.2. 6.6 and 9.8. We're at the end. That means I need to go down to 11.7 now. 11.7 and well, we already have 6.6 up here.
8.9.
So it'd be 8.9. 11.7 and 2.2. 11.7 and 9.8. We're at the end. So now I need to move it down to 8.9.
Oh, wait.
8.9 and 2.2. 8.9 and 9.8. Again, we're at the end, so I'll move it to the next one. 2.2 and 9.8.
That's the last one.
That's the last one. So now we need to go through and find all the sample means of each of those. So find X bar for each of these. And if y'all want to split it up to where one person just does each, let's see. So there's 10 of us in here. So why don't we do this? Instead of us all pausing to calculate it, Riley, you get the first one?
Let me get the X bar.
Yeah. Steven, calculate the second X bar. Melissa, the third. Brandon, the fourth. Justine, the fifth. Isaiah, the sixth. Tara, the seventh.
Did we just add them up in the bottom?
Add them up and divide by 2. Yep.
I thought I missed like a crucial equation.
No, we're just doing the average. Nate, let's do the 8th one. Yancey, the 9th one. And you'll calculate the average on that last one.
Did you want one already?
Sure.
I had 9.15 in the first one.
9.15, okay. 7.75, okay. 4.4, yeah. 8.2, good.
Oh, sorry. 10.3.
10.3. Okay. 6.95, good. 10.75, okay. 8. 5.55. Yancey. 9.35, and Will. 6. Good.
Wait, to lose? Doing it for everybody?
There's 2 of y'all in here. We happen to have 10 points. So we got through this way.
So we mix classes because there's not enough people in one class. Like,
There's not enough AP to have. Because it's just scheduling, and if they try to put all of AP in one class, then I mean some of the AP students wouldn't be able to take it because they're taking AP English or whatever the case may be.
yeah, I got you. I was just curious.
Yep. Okay, so now I want us to take these sample means, all 10 of them, put those, delete the 5 that you have in L1, put into L1, and run one variable steps. So you can delete the 5 that are in there, put just your sample means in, and run one variable steps on it.
Okay.
Okay, so what did y'all get for your mean?
7.54.
7.84?
Yeah.
You got 5.4?
I got 5.4. I must have put one in wrong. Let me go back and look.
I'll say it should be 8.4.
Oh, I see what it is.
Okay. What about your standard deviation? The 3 decimal places. 1.998. That's all right. Okay, so let me go. I'm going to go to the next slide. Okay, we did that. So how did these values that we just found compare to our original population mean and standard deviation? So how does our mean down here compared to our mean up here? Same.
Isn't that like the same property as, or the same reason as if you have two lists and you're trying to find the mean of both of them, you just add the two means together.
It's kind of going off of that one. And then what about our standard deviation? Is there anything that we notice? It decreased, yeah.
What does it mean by the samples of size 2 are possible? Is that just saying a pair or what?
Yeah.
Okay. So if it said size 3, it'd be combination of 3.
Yep, so standard deviation decreased. We don't really know, unless one of y'all can figure out how exactly it decreased. We just know it decreased somehow, some way. So let's keep exploring. Now let's up it. We want to get triplets. So now let's find all samples of size 3. And then we'll go from there. So back up, go back to my blank slide. So now we want to get triples. Instead of pairs, we want triples. We're going to take the same systematic approach though. So I'm going to freeze my first 2 in place. So 6.6, 11.7, and 8.9. Then we can do 6.6, 11.7, and which one's next after 8.9? 2.2. And 6.6. We're at the bottom of page 2. Where it says, now let's find all the samples of size 3. So let's see, 11.7 and 9.8. I'm at the end, so that means I need to let my 11.7 go and turn it into a 8.9. 6.6, 8.9, and 2.2. 6.6, 8.9, and 9.8. I'm at the end, I gotta let it go. So 6.6. What's next? 2.2 and 9.8. Now I'm really at the end of 6.6. I've exhausted.
Not really.
It'll be for like 15, 20 minutes.
Okay. So now we need to turn loose of the 6.6 and go with 11.7. So 11.7, 8.9, and 2.2. 11.7, 8.9, and 9.8. I'm at the end, so I go 11.7, 2.2, and 9.8. Let's see, how many do I have here? 1, 2, 3, 5, 6, 7. And you got one more. I'm at the end of my 11.7s, so now I have to go to 8.9, 2.2, and 9.8. Now I'm at the end. Okay, so I want y'all to take the same number that y'all did last time. So whether I had you do 2, 3, 4, whatever, take that same group and find the average of it. So, Stephen, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, whichever group you were last time, do that same group this time. And since Riley's out, I'll give y'all his. His would have been 9.067. Yes, we're going to do 3 decimal places. Should be 10.25. Let's add these up, hit enter, and then divide by 3.
I got 3.417. 6.7.
Should be 6.833. We want to add.
I think that one.
Are you that one, or were you?
Well, I was the third one.
You were the third one, okay. Let me double check mine to make sure.
6.8. Well, 3.
What did you get for the third one, Julissa?
I got 6.8.
For the third one, I got 9.366.
So I think I added the second one.
Gotcha. 9.367. Yep. Okay, number 4. 5.9. That one is a nice one. Number 5.
8.433.
8.433. Number 6. Yep. Number 7. Yep. Number 8.
10.123.
Number 9. And number 10. 6.6 or 6.7? Same process. Put them all into L1 and run one variable stats. And if you've done that, just to be ready for the next part that we're getting to, make sure you have your Z table out, please. Like if you put them into one variable stats and you got your mean and your standard deviation, that's your Z table. So what did you get for your mean? I feel like I've seen this number several times now. What about your standard deviation? 1.332, that's right. So that answered that question on the top of page 3. On the top of page 3, it asks what's the mean and standard deviation. Okay, so I'm going to go to the next slide, which actually puts this all typed up and nice and neat and all that good jazz. How do these values compare to the population mean and standard deviation? So, same mean as population. And standard deviation is lower again. I don't know about y'all, but I'm looking at this thinking, something smells kind of fishy here. I may or may not have intended that pun. So, what do we notice about the mean? What will the mean always be? The same. So the mean of the sampling distribution equals the mean of the population. Now, on the standard deviation, as sample size increases, so notice as we went from 2 to 3, your standard deviation went what? Down. So as sample size increases, the standard deviation decreases. Maybe you want to put a big number 4 if you're dual credit beside this one. What's funny is I say that and then you're like, yeah, I noticed that. The person that sat in your seat last period was the one that said, isn't this number 4? Must be something with that seat today. Okay. So these are actual properties of sampling distributions of X bar. The first rule says that the mean of sample means is equal to your population mean. That's rule 1. Rule 2 says that your standard deviation of sample means is the standard deviation of the population Divide it by the square root of your sample size. So this is your standard deviation of your population. The N is your sample size. So this rule will be exact if the population is infinite. And it's approximately correct if the population is finite and no more than 10% is included in the sample. So, for example, if our population, which is capital N, is 100, little n has to be less than or equal to what for this to be valid? Has to be less than or equal to 10 to be approximately correct.
Are there rules for this?
There's not really any rules if it's more than 10. Well, more than 10% at least. I mean, if our population is 1,000, you could be less than 100. But as far as 10% goes, that's what we want to use.
Why doesn't it work?
What's that?
Why doesn't it work?
It's if you look at the graphs kind of start separating.
Oh.
Like if you make it like you would if you were taking like a junior or senior level stats class, and they start making you look at graphs. You'll start seeing like at first it's really close, and then once you get to a certain point, they start spreading out and not being as accurate.
I don't have to worry about Z-scores on this part of the unit, do we?
No, really.
Like, as of like what we're learning today?
As of what we've done so far, no. Okay, now if we think back to our fish example, it's not correct because the sample sizes were more than 10% of our population. So standard deviation wasn't very accurate on our fishing example because we were more than 10% of the population. But that's kind of hard to sample half fish. So our example is more for illustrative purposes. Okay, so let's look at an example. So it says the paper, the mean platelet volume in patients with metabolic syndrome and its relationship with coronary artery disease. That's a mouthful of a title. Includes data that suggests that the distribution of platelet volume of patients who do not have metabolic syndrome is approximately normal, with a mean of 8.25 and a standard deviation of 0.75. So there's our nice, pretty graph it gave us. It went on and did it for us. So we can use a software called Minitab to generate random samples from the population. Y'all won't have to know how to do Minitab. If we get to do what I want to do, dual credit will learn R though.
Learn what?
R, statistical language R.
I don't have to learn R. Really?
It is. Because you get to take, hopefully you get to teach y'all how to take raw data of your interest. Maybe it's football stats, maybe it's, you could do like I did found a data set that talks about car crash deaths. Kind of morbid.
That's so morbid. All right, I'm done.
And then analyze it and see, oh, is this normal? Are there any relationships between the variables? Can this cause that? That's when you'll really get to see statistics in action. Okay, so anyways, we're going to use Minitab to generate random samples from the population. We're going to do 500 random samples of size 5 and compute the sample mean for each. And we're going to turn around and do the same for n equals 10, n equals 20, and n equals 30. Except I'll say we're going to do it. Really, they do it and give us the graph of it. So the histograms are the results of this. So first they ask us, if we look at these, what do we notice about the means? If I go through here and I find all my means, which is about there, roughly in that area.
They're all in the middle.
They're all roughly in the middle, but what value should they be centered around? What did they tell us the mean on the previous page? 8.25. So what do we notice about the means? They're all around 8.25. That's what we notice. I'm not going to write it up here just because I would have to erase it so I can get ready for the next question. But you should write it in your notes that they're all around 8.25. What do we notice about standard deviation? Remember, that's talking about how spread out the graph is. Look at this first graph, we're all the way out here. And I'm here. And here. And here. What do we notice about the standard deviation? As n increases, what happens to it?
Smaller.
Good. So as n increased, standard deviation decreased. And then, last question of this triplet, at least, of questions. What do we notice about the shape? They're all almost what?
Symmetrical.
They're symmetrical, but more particularly, they're normal. So, which normal is symmetrical? It's bell-shaped. Yeah. So, shape-wise, they're all approximately normal. Clearly, they have different heights, but they're still all bell-shaped or normal. Okay, so our next rule. We talked about 2 of them, now we have our 3rd rule. When the population distribution is normal, the sampling distribution is also normal for any sample size n. So if we start normal, it doesn't matter what n we pick, we will stay normal. We're not going to go to the dark side, even though I hear they have cookies. we can see that illustrated in this graph. So our population is this lower one. I'm kind of tracing out. That's our population. Notice our sample size. N was 4, N was 16. They just stayed normal. They just kept getting narrower. But now you may be wondering, okay, what happens if it's not normal? Well, let's look at an example of that. Anyone watch hockey, NHL? What were you saying, Nate? You watch it? So there's this paper that asks, is the overtime period in an NHL game long enough? And it gave data on the time in minutes from the start of the game to the first goal scored for 281 regular season games from 2005, from the 2005 to 2006 season that went into overtime. And they show us the density histogram. What do you notice about this histogram? They kind of tell you, but it's got a large positive U. Also, they tell us it has a mean of 13. So now we're going to do the same thing we did on the last example. We're going to use Minitab to generate 500 samples with sample sizes each of 5, 10, 20, and 30. That's on the next page. Well, they only looked at 2005 and 2007. Oh.
It was like 8 hours ago.
Oh, wow.
Yeah.
Kind of like the A&M LSU football game. That one, I think it was year before last. 2 years ago. Went into 7 overtimes. I had to drive back here to Lufkin the next morning. But I didn't care. I was staying up until 11 o'clock, whatever time the game ended, and watching it. My brother and his now wife were at the game and said it went into mayhem when we won the game. But a good time for them. Like all the Aggies just rushed the field, and LSU, he said they didn't even stick around. They just instantly headed for the locker room. All the fans left.
Oh, you're talking about the 7 overtime?
Yeah. It was insane. Like, you're not supposed to be on Kyle Field or any SEC field after the game. They didn't care. Like, everyone leaped over the wall, and then people started to GoFundMe to pay the fine that A&M was charged.
How big was the fine?
I can't remember what it was.
They got charged because they rushed the field?
Yeah. For all SEC games, no spectators are allowed on the field. But we didn't care. We were rushing the field anyways, because that was the first time we beat LSU since we joined the SEC.
And then the year after.
Yeah, let's not talk about that yet. Okay, so we did our graphs in Minitab. So what do we notice about the means? What are they all around? Or what should they all be around? They should all be around 13. Okay. What do we notice about the standard deviation? As n increased, the standard deviation got smaller. I don't know the answer to this, Nate. Does Houston still have a hockey team?
Houston.
Yeah.
I think
No, I don't think that. They have what's the, like minor league.
Ah.
Minor league.
And so they used to have the arrows.
They have a minor league team, but they don't have any. The
Gotcha.
only major league one you're interested in.
Oh, it's okay. But when I was in, I guess it was 4th grade, we went to an Arrows game, but then I don't think they ever did really good, so they just dissolved the team or sold it somewhere. What do we notice about the shape of these histograms? So what kind of happens? At first, I'm still skewed, but then as we increase, what starts happening? We start getting more and more normal. So as n increases, they start becoming normal. Which leads us to rule number 4. That's one of your bigger rules in statistics. I remember when I first learned it. It's called the central limit theorem. So when n is sufficiently large, the sampling distribution of x bar is approximated by a normal curve, even when the population is not normal itself. But what do I mean when I say sufficiently large? Well, we can safely apply it if n exceeds 30. If n equals 30, then we're approximately normal. Okay, so let's look at our example. As a soft drink bottler claims that on average, cans contain 12 ounces of soda. Let X denote the actual volume of soda in a randomly selected can. We're going to suppose that X is normally distributed with a standard deviation of 0.16 ounces. And we're going to select 16 cans to sample. So if the bottler's claims are correct, then the sampling distribution of X bar is normally distributed with what? Well, we need 2 things. We need our sample mean and our sample standard deviation. Or, sorry, we need the mean of the sample means, the standard deviation of the samples. What do we know about the mean of the sample means? What's it always equal? It will always be 12, our population mean. I'm going to actually write that here. Now, To get the standard deviation of our sample means, what do we have to do? We have to divide the given standard deviation by the square root of our sample size.
So why did you do mu of x equal to mu plus 12? Like, why did you say that like that?
Because our formula tells us that the mean of the sample means is equal to the mean of the population,
Okay.
which is 12 in this case. So what I'm doing is I'm just stating our formulas that we're going to use.
X bar is sample or population?
X bar is sample mean. So the mu of X bar means that's the mean of all of our sample means. Make sense?
Yes, sir.
Okay, so my standard deviation of the population, they tell me, is 0.16. Now I need to take the square root, divide that by the square root of my sample size. What's my sample size here? 16. 0.16 divided by the square root of 16 gives you 0.1. 04. Okay, so if the bottler is correct, then the sampling distribution of X bar is normally distributed with the sample mean, the means of 12, and sigma is 0.04, which is what that says right there. So now, let's find the probability that the sample mean soda volume is between 11.96 ounces and 12.08 ounces. This is where we're going to need our z-tables. So we want the probability that X bar is between 11.96 and 12.08. Since we can assume it's approximately normal, actually, wait a minute. No, they tell us that. They tell us this time it's approximately normal. What do I have to do first before I can use my tables? Standardize, good. I'm going to find the probability that 11.96 minus 12 divided by 0.04 is less than z, which is less than 0.08 minus 12 divided by 0.04. So what's my lower z going to be? If I simplify this, what would I get? It should be -1, that's right. What about my upper bound? 2. This needs to be a z right here. Not an x anymore. Okay, so remember on these, we have to subtract the big probability from the small probability. What's the probability that z is less than 2? 0.9772 minus, okay, what's the probability that z is less than -1? 0.1587. And if we subtract those, we get 0.8. 0.8185. There we go. There's our probability. Now, I forgot to say this last period, but I'm going to test. See how many people silently just wanted to like stick a dagger in my desk. They were giving me probabilities greater than 1. They were giving me probabilities that said 20.96. Like, probability can't be bigger than 1. That should have been a red flag that that answer is not right. Okay, anyway, let's get through this last example. Hot dog, get your hot dog. So, speaking of hot dogs, a hot dog manufacturer says that one of his brands has 18 grams of fat per hot dog, with a standard deviation of 1 gram. As you can probably imagine, consumers wouldn't be disappointed if that was less than 18 grams. But you probably don't want more than 18 grams of fat in your hot dog. So an independent testing organization is asked to analyze a random sample of 36 hot dogs. Suppose that the resulting sample mean is 8.4 grams. Does this suggest the manufacturer's claim is incorrect? It's above 3 what? That's right. Well, let's walk through it. So, sample size is greater than 30, so we can use our central limit theorem. So that applies, which means we're going to use a mean of 18, because remember, we want to test what the manufacturer says. They say there's 18 grams of fat with a standard deviation of 1 gram. So our mean here will be 18. To get our standard deviation, we have to do the one they say divided by the square root of our sample size. So that's going to be 0.1667 is our standard deviation that we're going to have to use to test their claim. Are y'all ready to put it to the test? See if they're telling the truth? Okay, so let's test this claim. We want to find the probability that X bar can be greater than 18.4 grams. Greater than or equal to 18.4. I mean, if it's a high probability, then he may be telling the truth. I say he. I did that last period. We're just going to blame the CEO on this. It's all his fault. Okay, so since we can use the central limit theorem, that means that we're assuming this is approximately normal. So let's get our z-score. This is going to be the probability that z is greater than or equal to 18.4 minus 18 divided by 0.1667, which is the probability that z is greater than or equal to what? 2 point what? 2.40. But does our table give us the probabilities for greater than? No, so we need.
1 minus Z is less than or equal to.
That's right. So it's going to be 1 minus what? 0.9918. Which equals 0082. So what this tells us is that sample means greater than or equal to 18.4 will only occur .82% of the time.
Sounds pretty good.
So if that's the mean that they found,
0.8, oh yeah.
so this mean is large enough for us to doubt they're 18 grams. Because remember, we took a sample of 36 and got 18.4 as our mean. And that should only occur 0.82% of the time. So this is large. This mean is large enough to cause us to doubt the manufacturer. Yes. Can we wait until the bell, please? And we're done. So dual credit, this should be enough to complete 5 course. That's why it's due on Thursday. I don't have it in Blackboard yet, but seeing that not many have started the ones due tonight, I don't think that should be too big of an issue right now. I'll get it in Blackboard tonight. Yeah, the one from my area. Put them up here. Someone sits here next to you. Yeah, I try to have them positioned at the ready.
I got it.